Hello there. Welcome to this video on using the IoT communication protocols. In this video, we're going to see an IoT device communication scenario. We're also going to see how an IoT microchip should look like and what are its characteristics. We're going to see what are the protocols today used for general purpose communication. We will also emphasize on the protocols suitable for IoT devices. Alright, let's get started. Now the first thing we want to establish is the edge devices. Now edge devices are basically your IoT endpoints. Now these could be your IoT devices, your sensors, your development boards and so on. Now in a large perspective, these devices are categorized into two large categories. One is the consumer IoT devices and the other one is the embedded IoT devices. Of course, there could be other categories as well. Now, the consumer IoT devices are basically your Nest thermostats, your home automation IoT devices, your smart shirts, your smart utilities. All of these will come under consumer IoT devices. The embedded IoT devices are the ones which are living deep inside machines, which live on independent sensors, and in other use cases like industrial IoT, in smart manufacturing, and so on. Alright, now we know what is an edge device and two different categories. Now the whole point of an IoT device is that it should establish communication to the internet. Now before the device establishes a connection to the internet, it first talks to a local area network. So those are your LANs, WANs, using wired or wireless like Bluetooth, Wi-Fi, or you could also use a power line. So depending on your scenario, your use case, you can use different methods to communicate to a local area network. So this will essentially become somewhat of a gateway to talk to the World Wide Web or the internet. So from that point, you communicate to the internet. So on the internet, so you're either communicating to an Internet of Things platform like, for example, ThingWorx, Carriots, IBM has one, Cisco has one. Many of them have IoT platforms today. Or you are communicating to an application built specifically for your set of devices. Or your device could be communicating to other cloud services. Okay, now once your devices are connected to the internet for whatever reason and to whatever platform, then there is a set of activities which go on. The first is you acquire the data, you derive value from the data, and you enable the end users to take some action. So finally, on this side, it is used at the end user area. So who are your end users? So it could be a company which wants to derive analytics, which wants to take decisions, which wants to automate things, which wants to make certain processes smart and efficient. It could be end users like you and me using a phone application to switch on and switch off your devices at home. Or it could also be other sensors and machines using this information. Now let's zoom on the edge device and the local network area. So an edge device could directly connect to the internet after a set of ISP layers, or it could first communicate to a gateway, and then the gateway can communicate to the internet, or different gateways can communicate to a local cloud or an intra-cloud, and this cloud can actually communicate to your IoT platform living on internet or any other service living on the internet. So there are multiple ways how your edge devices could land up communicating within themselves and with the internet. Now let's look at the characteristics of a microchip which could be used to power an IoT device. The first thing is the power. So it should be consuming low power as much as possible, because these microchips will be living in devices which will be mostly in remote locations or as a part of a machine or as a part of a sensor. So in most times, conventional way of powering this device is not possible. So you got to be relying on batteries, and hence you should be using low power. It should be low cost because the application is wide and heavy. So you could be needing plenty of these to actually make sense of the solution. And it should have a good range so that it can communicate with other devices to a gateway or to a router. Now, a couple of offerings today in the market are by Atmel, by ARM, by Intel. Of course, there are other players as well. These are some of the top ones. So Intel has chips like Atom, Quark, ARM has a complete Cortex M series, and Atmel has its own set of microchips. Now, these are the hardware players. Companies like Microchip, they use an ARM Cortex chip and they add the software layer on top of it. Another player in the market is called Particle. Particle also uses the ARM Cortex chip and it has its own IoT platform which the chip is automatically programmed to hook up to. So the whole plumbing is solved by Particle, so it's very easy for the developer to develop an IoT application and to provision it in a relatively short amount of time. Of course, there is a cost factor to it. Last but not the least, you have the development platforms like Arduino and Raspberry Pi, which allow you to learn IoT, and of course you can also use these development platforms in some applications, but most likely not in production for consumer use. Development platforms are very friendly. They have the microchips and they have the software and they have other protocols built in it. They make it easy for you to communicate with them. They make it easy for you to power them, so you can power them with USB and other plenty of features which a development board should have. Now let's take a look at the IoT device communication protocols. In other words, this is the software part of the equation. Now, protocols currently available today are written for general purpose devices. They're not written for devices with constraints like the IoT devices. So naturally, they use more power. They send more data in the same sample because the header repeats in every transfer and other overheads. It takes more time to send the data because you tend to use a lot of layers of software, and naturally it uses more RAM and ROM space. Now, a typical protocol for an IoT space should use minimum power. It should send less data for the same sample, so it should manage its header space nicely, and it should also reduce the overhead. It should take less time to send data. It should manage its sleeping time nicely so that they can consume the power. It should have very less lightweight layers of software, which is essential for the device, and of course it should need less RAM and ROM space because of the space constraints. Let's take a side-by-side look of protocols for general purpose and IoT specific scenarios. In the internet and network layer, we could switch to 6LoWPAN, which is basically a low power wireless personal area network which understands IPv6. We could switch to UDP, which has much less overhead compared to TCP. On the web transfer layer, we could use co-op, which works on top of UDP and has much less overhead compared to HTTP. On the application layer, we could use existing technologies like REST APIs, JSON objects, and so on. Let's take a look at some existing technologies which can be used in IoT scenarios. In the network layer, you have Zigbee, which has been there for a while. It's used for local area network communication, and Zigbee IP understands IPv6. Z-Wave is similar to Zigbee, and it is somewhat proprietary in nature. Coming to the web and application layer, we have MQTT, which uses a publish and subscribe model. It is very lightweight and can be used for IoT applications. You have WebSocket, which is developed by the HTML5 consortium. It has a full duplex open socket communication, and it solves much of the complexity around client-server communication. You also have XMPP, which specializes in instant chat, peer-to-peer communication, one-to-many communication, and it can be extended for other scenarios as well. Of course, this is not a comprehensive list, and there are many other technologies out there which can be used for IoT scenarios. In the next video, we're going to be testing Arduino Uno, Ethernet board, and Node MCU. Thank you.